So welcome to the lecture 5 of electric charges and field. So today we will be dealing with the application of Gauss law. So in the previous lecture we read about electric flux. So now we will be dealing with the application of Gauss law. So we have discussed about the fact that the Gauss law states that the electric flux is equal to cyclic integral of E dot A, which is equal to the charges enclosed inside the closed Gaussian surface divided by epsilon naught. So over here, while calculating the value of electric field using Gauss law, we need to select a particular type of Gaussian surface such that either the electric field and area vector are parallel to each other or they are perpendicular to each other. Just to make sure that we can omit the cos theta part. So if we begin with this application, so we are dealing with the first one, that is electric field due to infinitely line charge. Due to infinitely large line charge. So if we take this system into consideration, so we are considering something like this, that we have a very large, infinitely large line charge, something like this, and the positive charge is spread throughout this line charge with the value equal to lambda charge per unit length. So in order to solve this, we are selecting a Gaussian surface. So the Gaussian surface which we are using over here is cylindrical. This system has a cylindrical symmetry. This property suggests that we are using a cylinder as a Gaussian surface with an arbitrary radius and length. So I am considering a cylinder with the line charge located at the center of this cylindrical axis. So now one thing is clear over here, that the electric field due to this line charge will be directed in the outward normal like this, such that the direction of electric field is parallel to the area vector of the curved surface area of the cylinder. So the direction of electric field is along the curved surface area of the cylinder. That if I select a patch at the curved portion of this cylinder, the direction of area vector and that of the electric field is in the same direction. And on the top surface, the area vector is along the outward normal. This is the area vector, and in the lower surface, it is in this direction. That is along the outward normal. That is area vector is in this direction. So if we talk about application of Gauss law, so we are considering that the length of this cylinder is L and the radius is R. So if I consider the charge enclosed inside this system, then I can say that the charge enclosed is equal to lambda times L, because lambda is charge per unit length and the length of the cylinder is L. So if we apply Gauss law, so I can say that the electric flux through this top surface is through this top surface, bottom surface and the curved surface area will combine together to give us the total electric flux, that is equal to Q enclosed by epsilon naught. Now due to the top surface and the bottom surface, I can say that the electric field is perpendicular to area vector and hence the contribution in electric flux will be 0. So due to the curved surface area, the value of electric field and area vector is in the same direction. So we can write it as E into 2 pi RL, which is equal to lambda L upon epsilon naught. So from here, we obtain the value of E, which is equal to lambda upon 2 pi epsilon naught R, or it can be written as 2k lambda by R. So due to an infinitely line charge, the value of electric field is equal to 2k lambda upon r. So we are calculating electric field at a distance r. So this one was the first example of using Gauss law. Let us move to the next example. So this time we are calculating electric field using Gauss law through an infinite plane sheet of charge. So this time we are doing it for electric field due to infinite plane sheet of charge. So we are considering something like this, that there is a infinitely large sheet which is having a positive charge distributed over it. Now since this time we are having a sheet, so the representation will be done using sigma, that is charge per unit area. So charge is distributed throughout the area, so we are taking sigma charge per unit area. Now in order to consider this consider a Gaussian surface for this surface, we are using a pillbox symmetry. Now when I refer to a pillbox symmetry, I mean to say that we are selecting a cylindrical Gaussian surface which is inserted through this sheet like this. So we are selecting something like this, and I am representing this with a dotted line. So we are using something like this as a Gaussian surface for this particular system, which we consider as an example of a pillbox symmetry. Now since this sheet is infinitely large, so somewhere at the center of the sheet, the electric field due to the positive charge will be directed away, that is in this direction. So the direction of electric field is E vector along this, and from the back surface also it will be E vector, that is directed away from the positive charge. And if we consider the area vector, then for this cylinder or the pillbox, we consider that this surface or the top surface will have the area vector in the direction of electric field, and the back end is also having the area vector in the direction of electric field, and the curved surface is such that the area vector is perpendicular to the direction of electric field. So we can say that due to the curved surface, the electric field and area vector are perpendicular to each other, and hence the contribution in flux will be zero. So if we apply Gauss law, that is cyclic integral of E dot A is equal to charge enclosed divided by epsilon naught. So if we have considered this patch is of area A, so the value of charge enclosed can be written as sigma into A divided by epsilon naught, which is due to the entire area of the pillbox. Now since only the top surface and the bottom surface is contributing the for the electric flux, so I can write it as twice of EA is equal to sigma A by epsilon naught. The value of electric flux through this curved surface is going to be 0 because electric field is perpendicular to the curved surface area, and hence from here we obtain that electric field is equal to sigma by 2 epsilon naught due to this positively charged sheet. So our assumption that the sheet is infinitely large is an idealization. Nothing in nature is really infinitely large, but the result E equals sigma by 2 epsilon naught is a good approximation for the points that are very close to the sheet compared to the sheet's dimensions and not too near its edges. At such points, the field is very nearly uniform and perpendicular to the plane. So over here, I am introducing one more notable point to be noted, that if we consider the two such infinitely large sheet with opposite polarity kept near each other. Suppose I consider a plus sigma charge sheet and a minus sigma charge sheet placed close to each other. So due to the positive sheet, the electric field will be directed away. So E due to the positive sheet will be directed away, that is in this direction. Over here also it will be in this direction, and on the left also it will be directed away, that is in this direction. And the value of each is going to be E is equal to sigma by 2 epsilon naught. E is equal to sigma by 2 epsilon naught, and E is equal to sigma by 2 epsilon naught. And due to the negatively charged sheet, I can say that the electric field is directed towards, that is something like this. Towards the right hand side it is directed towards, and on the left hand side also it is directed towards. So E due to the negative charge is also equal to sigma by 2 epsilon naught. The only difference is that it is directed towards. So E is equal to sigma by 2 epsilon naught, and again E is equal to sigma by 2 epsilon naught. So if we consider the net effect, so the value of electric field over here will become 0, that is the two electric field are in the opposite direction having equal magnitude, will crisscross each other, and the electric field or the net electric field will be only between the plates, and the value of electric field will get added to each other, that is it will become sigma by epsilon naught. This arrangement is regarded as a capacitor, and we will read about it in detail, that if there are two sheets, one positively charged and the another negatively charged, then the electric field is located in the region between this sheet, and the value of this electric field is going to be equal to sigma by epsilon naught. So now it must be very well kept in mind that when there are two identical sheets, then the value is sigma by epsilon naught having same surface charge density. Otherwise, the value due to a single sheet is only sigma by 2 epsilon naught. It must also be noted that if the two sheets are having opposite surface charge density, then the value of electric field will be different. It will become sigma 1 by 2 epsilon naught plus sigma 2 by 2 epsilon naught. So these things must be very well kept in mind. So let us deal with the next example. So we are dealing with electric field due to a shell. Due to a shell. So if we consider a shell which is having a charge distributed over it, so we are considering something like this. So we are considering that the charge Q is distributed uniformly over the surface of the shell, and we will be calculating electric field inside and outside the shell. So if we select a Gaussian surface inside the shell, that is somewhat like this, at a distance r from the center. So over here I am taking that the total charge Q is distributed over the surface of the shell. So if I write inside the shell, so I can write that the charge enclosed inside the shell is 0, and hence the electric field inside the shell, cyclic integral of E inside dot A, is equal to Q enclosed by epsilon naught. So E inside is going to be 0. Now if we select another Gaussian surface outside the shell, that is somewhat like this. So our choice of Gaussian surface this time is spherical. It is because the electric field due to a spherical shell will be in the radially outward direction, and at every point on this sphere the direction of electric field and area vector will be parallel to each other, and hence it will be convenient for us to calculate the value of electric field using Gauss law. Since E and A are parallel to each other, so our choice of Gaussian surface is a sphere with its center coinciding with the center of the charged shell. So over here if we apply for outside the shell, So this time I say that the charges enclosed is equal to the total charge on the shell. So the total charge on the shell will become the enclosed charge, and hence if we apply cyclic integral of E dot A is equal to Q enclosed by epsilon naught. So from here I can say that E outside into 4 pi r square is equal to Q upon epsilon naught, and hence electric field outside is equal to Q upon 4 pi epsilon naught r square. Or I can say that outside the shell it is behaving as if a point charge Q is placed at the center of the shell. So the value of electric field is just like a point charge, that is kq by r square, with the charge being placed at the center of the shell. If we look at the graphical representation for this particular arrangement, so I can say that if this is representing the electric field on the y-axis and the distance on the x-axis, so the value of electric field is 0 inside the shell, and outside the shell the value is equal to kq by r square, and it is decreasing like this. So this is how the value of electric field is evaluated for the surface. And if we consider on the surface of the shell, so many a time the problem is given in terms of sigma. Sigma is equal to q upon 4 pi r square. So we can also write it as sigma by epsilon naught. So there is no need to panic when such a question is asked, that for a shell they have given sigma. So you can simply do it that charge per unit area, that is 4 pi r square, can be written as sigma upon epsilon naught. So the value on the surface of the shell for the electric field will be sigma by epsilon naught, and then at any point outside can be simply written as kq by r square, where r is the distance measured from the center of the shell. So let us deal with the next example, where we are calculating electric field due to a charged sphere or a sphere studded with charge. Due to a sphere studded with charge. So if we consider a sphere studded with charge, so our selection of Gaussian surface is going to be spherical symmetric, for the same reason which we have explained due to a shell. So this time the enclosed charge inside the sphere will also have some charge enclosed inside it. So we are considering that the sphere is an insulating sphere, and then only it is possible that the charges will stay inside the sphere. Otherwise the charges will flow and come to the surface of the sphere. So we are considering a sphere like this. So we can say that the charge is distributed throughout the volume of the sphere. So the positive charge is distributed throughout the volume of the sphere. So in this case we will be using the value of rho, where rho is equal to charge per unit volume. So we will be using the value of rho for this particular problem. So at any point inside the sphere, that is somewhat like this, at a distance small r. So we are considering that the total charge on the sphere is capital Q and the radius is r. And if we are considering a Gaussian surface inside at a distance small r, so I can calculate the charge enclosed in this way, that rho equals capital Q upon 4 by 3 pi r cube is equal to Q enclosed upon 4 by 3 pi small r cube. So we are calculating for the time being in terms of rho. So I am calculating Q enclosed as equal to 4 by 3 pi rho r cube. So if we apply Gauss law, then I can say that E dot A is equal to Q enclosed by epsilon naught, and hence due to electric field inside, I can say E into 4 pi r square is equal to 4 by 3 pi rho r cube by epsilon naught. And the value of electric field inside this sphere studded with charge is obtained as rho r by 3 epsilon naught. So this is how we solve at a point inside the sphere. If you wish to put rho in terms of the total charge, then we can modify this expression in this way as well, that we can write it as rho can be written as q upon 4 by 3 pi capital R cube and then upon 3 epsilon naught. So we will get this term as rho r by 4 pi epsilon naught R cube. So this is also one possible equation for electric field inside an insulated sphere studded with charge. For any point outside the sphere, so for any point for outside the sphere, if we select a Gaussian surface, then we can write it as cyclic integral of E dot A is equal to Q enclosed by epsilon naught, and the value can be written as E into 4 pi small r square is equal to capital Q by epsilon naught. So the total charge of the sphere will get enclosed inside the Gaussian surface, and the value of electric field will come out to be 4 pi epsilon naught r square. So the entire insulating sphere studded with charge will behave like a point charge q, which is situated at the center of the sphere. So if we consider this portion and we try to draw a graph for this arrangement, so I can say that for a point inside the sphere, the electric field is proportional to the distance r from the center, and hence the graph is going to be somewhat like this, that it is going to be rho r by 3 epsilon naught. So it is proportional to r, and outside it is inversely proportional to r square. So this is going to be the graphical variation of electric field with r for a sphere studded with charge.